Okay, I'm going to talk about kind of a hard problem, which is to evaluate a particular double integral in polar coordinates. And because the reason it's hard is that it needs splitting of regions. It's not gift wrapped, so to speak. So the problem, it's similar to one in the book, and it looks like this. Find the area enclosed by two curves. First we have x squared plus y squared equals 1, and next we have x squared plus y minus 1 squared equal to 1. If only that 1 wasn't there, then this should be a very easy problem. So let's break this down into several steps. The first step is just to draw the regions. Okay. 1 I can do pretty quickly, right? That's circle radius 1, or at least my approximation of it. And we can draw a shifted circle, shifted up by 1. And then the region that we want lies in between. So you'll see why this is kind of hard in a minute, but I'm just going to lay out the steps that I would do to solve this. And this will hopefully systematize the process for you. So the second step is we need to polarize everything, right? This is all xy stuff. So xy to r theta, everything. So first of all, if we call this A, we call this B. A is just r squared equals 1. So really that's just r equals 1. B is a little harder. Let's just write it out. It's x squared plus y squared minus 2y plus 1 equals 1. We can cancel the 1's, and we can simplify this to r squared. So we end up getting r squared equals 2y. If we continue the plug of polar coordinates into Cartesian, we get 2r sine theta. So that means r equals 2 sine theta. So when I said everything, I meant everything, including the graph. So we plot r as a function of theta. So 2 sine theta will look something like this. And 1, well, it's just 1, right? So not much to draw here. And a key point is that we restrict to r greater than 0. So I'm ignoring everything out here and over here in the graph. So we don't want to deal with negative radiuses, right? So the next step is I'm also going to look where they intersect. So on the graph, it's pretty close to pi, and this is pretty close to 0. And it's when r equals 1 intersects with r equals 2 sine theta, or in other words, whenever sine theta equals a half in our good range of r equals 0. So that happens when theta is pi over 6 or 5 pi over 6. If you have trouble seeing why it's 5 pi over 6, just note that it's pi minus pi over 6 because you have symmetry over pi over 2. Okay, so we have our intersections at pi over 6 and pi over 6. You would think that we're ready to start integrating, right? Because we have our theta min, our theta max, our r min, and our r max, right? Well, it turns out if we try just plugging it in to the integral, we get wrong stuff. And that's because it doesn't correspond to the right region. So for example, if I'm just going to redraw it really quickly. So here's what we have. If I tried to integrate that, then what does this correspond to on the xy plane? This is, remember, this is the r theta plane. So now if I look at the xy plane, and this corresponds to 2 sine theta being on top and 1 being on the bottom. So here's 2 sine theta, and then here's 1. So we're actually integrating this top portion up here, whereas the one we really want is the bottom portion inside r equals 1. So we would have gotten the wrong integral if we did that. That is to say, the orange region is wrong. So how do we fix that? Okay, I would say the third step, I think we're on 3, right? We're on 4. So the fourth step is to think, well, what are the regions that are available to us by integration? So draw the integration regions. Or rather, make a note. So if we redraw this yet again, and we compare with the r theta plane, this is yx, then we have 3 distinguished regions, right? So here's 1. Here's 2. 2 is in the middle, and then 3 will be at the end. And if we go backwards, then we see 3 is near pi. We see 2 is in the middle. And we see that 1 is close to 0 in terms of angles. So, and let me just indicate 1 by shading it with red. And I'm going to shade 3 with green. And I'll just briefly shade 2 with orange, just to see what we can get by taking integrals. Now what we really want is, what we really want is brown, is the brown region. So I'll denote that by star. So now the 5th step is to use geometry to write star what we want in terms of 1, 2, and 3. Okay. And so this is region, and so what we're doing is now we're splitting regions up. So how I would do this, well, you could actually do it several ways. So I'll tell you both ways. So first of all, star, we could think of it as part of the shifted circle. So you could say that star is the area of the shifted circle, area of the shifted circle minus 2. 2 is the orange region. Okay, but we could also do it another way. We could do it as half the area of r equals 1 circle minus the piece near 0 and minus the piece near pi. Right? So we have two ways that we could compute star, but the problem is both require subtraction from a geometric quantity. So both require subtraction from areas of circles. And we're subtracting the integrals. Okay, and the integrals themselves aren't that bad. So I'll leave that to you if you want to practice that. But I think the really non-trivial part was having to set this up and comparing and getting the geometric intuition. The reason why I showed you the r theta plane is it helps you sort of see what the relative positions of the curves. So which curve is above the other one. So, and these are, of course, the limits of your integral. So I would draw both if you have time. Okay, I hope that is helpful. Thanks for watching.